Problem A2. Solution for this problem you can find below this video in the reference of the description. An ideal but not necessarily perfect monatomic gas undergoes the following cycle. The gas starts at pressure P0, volume V0 and temperature T0. The gas is heated at a constant volume to a pressure alpha P0 where alpha greater than 1. The gas is then allowed to expand adiabatically. No heat is transferred to or from the gas to pressure P0. The gas is cooled at a constant pressure back to the original state. The adiabatic constant gamma is defined in terms of the specific heat at a constant pressure Cp and the specific heat at a constant volume Cv by the ratio gamma equal Cp over Cv. Questions. A. Determine the efficiency of this cycle in terms of alpha and the adiabatic constant gamma. As a reminder, efficiency is defined as a ratio of work out divided by heat in. B. A lab worker makes measurements of the temperature and the pressure of the gas during the adiabatic process. The results in terms of T0 and P0 are in this table. Plot an appropriate graph from this data that can be used to determine the adiabatic constant. C. What is gamma for this gas? Solution. As we can see on this PV diagram, we have isochoric process from point 0 to point 1. After that we have adiabatic expansion from point 1 to point 2. And after that we have isobaric compression from point 2 to point 0. Now let's count all these parameters PVT for each point. In point 0 we have parameters are P0, V0, T0. In point 1 we have the same volume V0, but due to proportionality of pressure and temperature for isochoric process, we have pressure is alpha P0 and temperature is alpha T0. During isochoric process from 0 to 1, that was heat Q01 added to this gas, which is number of moles multiplied by heat capacitance Cv multiplied by temperature difference. So that will be NCV multiplied by alpha minus 1 T0. After that, using formula for adiabatic expansion, connecting pressure and the volume, we can find what is volume in point 2 using this formula. We can use known numbers alpha P0 for P1 and find what is V2. So we have V2 equal alpha power 1 over gamma multiplied by V0. Next step, due to proportionality of temperature and volume during isobaric process from 2 to 0, we have temperature T2 equal alpha power 1 over gamma T0. And now we can count what is the heat transfers during process 2 to 0. That will be number of moles multiplied by heat capacitance for constant pressure and multiplied by temperature difference T0 minus T2, and that's equal this expression. Now we can count what is work done by gas. That's Q01 plus Q20, which is equal to this expression. And last step is to find what is efficiency. Efficiency is work done by a gas, which is W divided by Q in, which is Q01. So finally efficiency equal work done by a gas over Q01, which is 1 minus this expression, where gamma is a relation between Cp and Cv. Question B. A lab worker makes measurements of the temperature and the pressure of the gas during the adiabatic process. The results in terms of T0 and P0 are in this table. Plot an appropriate graph from this data that can be used to determine the adiabatic constant. For adiabatic process, we have this expression is constant. It means that we have this expression for adiabatic process. Now let's take a logarithm from both parts. Now we have this dependency that this logarithm equal some kind of coefficient which we can call slope multiplied by this logarithm. And because we have this data, we already have this relation as a table, and we can plot this graph and count what is the slope of this graph. From this graph we can find that this slope equal approximately 3.5, and it means that gamma equal 1.4, and this gamma related to diatomic gas. That was actually an answer for question C.